Okay. So we tried to prove, suppose the following theorem, right? We are assuming ADR plus V equals L of PR, but I don't. Oh, he's joining. Why is he? I said he just told me he had a class and now he's joining. Or maybe he's joining from his class. Olaf, are you joining from while listening to your other lecture? Right? Okay. So let mu be the Soloway measure or the supercompactness measure on P omega 1 of R, right? So it's the club filter, the one that 1 and 2 play reals, and then the set is measure 1 if the play they produce belongs to the set. I mean, player 1 has a winning strategy in that game. Okay, so it's a supercompactness measure. Then I mu omega 1 is equal to theta. Okay, so this is what we want to prove. I don't know who proved it, probably wouldn't, but maybe Soloway, I don't really know. I didn't prove it. Yeah. Okay, so what is it that we want to do? We want to prove two things, right? So enough to show, as always. One by mu omega 1 is less than or equal to theta, and of course theta is less than or equal to pi mu omega 1. Now we're gonna use like this is a fundamental fact, right? I mean, this is something extremely basic in this theory. So it comes. So of course we use basic things to prove it. For example, some notation. Suppose A is a set of reals. Sigma is a countable set of reals, right? And okay, let me put A on the top and sigma in the bottom. Let's call this thing L A intersection sigma. Okay, so the thing that you want to say about this model, the following: for every A, the set of sigma such that the reals of MA sigma equals to sigma, that has measure 1. So for measure 1, many sigma are kind of full. Why is that? Well, imagine a new real shows up, right? So suppose otherwise, right? Suppose the set of sigma such that the reals of MA sigma is more than sigma, right? Sigma is there, of course, so this is...
Krugor, one quick question. When you say then MA sigma, you're actually defining MA sigma, or is it some fixed notation?
That's the notation. MA sigma is this.
Yeah, I mean, I was confused by the word then, right?
Then let, okay.
Yeah, sorry. I was, because like it looks like it might be something meaningful. Okay.
Okay, so suppose we did get a new real. If you get a new real, then it's definable somewhere, right? So let alpha be list alpha sigma. Let's call this set B, right? Now for sigma in B, let alpha sigma be released such that this new real is definable over that level, such that there is a real definable over L alpha sigma A intersection sigma sigma, right? I mean, this is the L hierarchy. So remember, L round bracket X means you put X at the very bottom, your L0 is X, and then you do the definability hierarchy, right? So if there is a new real that shows up, which is not in sigma, so you didn't put it at the very beginning, that means it's definable at some stage in that hierarchy, right? So it's definable at alpha sigma. Okay, if it's definable, that means that how can you define it? Well, what can you use to define it? You have to use objects in this model, but any object in this model is definable from that thing, A intersection sigma, and then members of sigma. Yeah, so you can mention A intersection sigma, sigma, and their members, and you can mention ordinals. That's any other object would be itself definable already from those three. So the three parameters that we need to care about are So the three parameters that we need to care about are A intersection sigma, sigma, and their members, and ordinals. So 4 parameters. Sorry. Okay, so that means now let P sigma. Well, P will be some finite sequence of ordinals. X. Well, I will not put X in there. Be such that for some X in sigma, right? P sigma, be such that for some X in sigma, A, this P sigma is a finite sequence from alpha and B. P sigma, or let's just say N is in Y if and only if L alpha sigma A intersection sigma in the sigma things P sigma N P sigma A intersection sigma and sigma and X. I'm allowed to mention X, right? Then Y is not in sigma, right? I can fix the formula. I can fix the parameter, right? Why can I fix the formula? There can be other formulas as well, but I can always pick the least formula in the enumeration of formulas are natural numbers, right? So you can always pick the least formula for which you could do this thing. Why can I fix the ordinal parameters? For the same reason, because there could be other ordinal parameters for which they would allow me to define a new real, but I can minimize them. So pick the least one. So these two I can fix. What I cannot fix by minimizing is the real. This real parameter. But I can use normality to pick a real, right? Okay, so now let F from B into reals be such that for every sigma in B, F of sigma is a subset of sigma, and F of sigma consists of the set of X in sigma such that P sigma A intersection sigma X defines a real over that is not in sigma. Okay. So f of sigma is the set of all these things. But then what do we have? Then we have, it's a subset of sigma, so by normality, right, since P has measure 1, there is a particular X 0 in R such that the set of sigma in B, let's call this C, such that X0 belongs to f of sigma, right, as measure 1. So for measure 1, we can fix the parameter. And okay, but now we get a contradiction because why do we get a contradiction? Because the real defined is now just a countable set of things, right? So you look at all the sigmas for which n belongs to. Is it clear why we are done? Now it's countable completeness of the measure. Some feedback, guys.
Like, I would like to ask firstly, like, why, what is the origin of this phi sigma and p sigma in general? Like, I understand we use here some constructibility, but I'm not sure in which way.
Right. Constructibility says what at the next level, right? So here's recall now X is what? We start with L0X, which will be, let's say, transitive closure of X union. Okay, so yeah, that's your, so at the beginning you put X and all the things in the transitive closure of X. Then L alpha plus 1X will be the definable subsets of L alpha X. Definable means, yeah, we have a formula and you're allowed to use parameters. And the limit steps, you just take a limit. This is sup alpha less than lambda, L alpha X, and of course L of X is just the union of L alpha X.
Yeah, okay.
Right. Now the key point is, now suppose, right, so suppose there's a new set, right? Suppose A is definable over L alpha X with parameters in L alpha X. Now what are parameters? Parameters will be members, right? So we have, well, I guess this is not the key point. The key point is that I have a sigma 1 function. The key point of the constructibility, there exists sigma 1 definable f from positive closure of X union X into cross ordinals into fix and alpha, right? I guess you want to say for every alpha. Let me erase it even. we want to say for every alpha that exists, sigma 1 over L alpha x. So sigma 1 definable over the structure F, which maps transitive closure of X union X plus alpha finite sequences from alpha into L alpha X, such that F is surjection. So basically, every member of L alpha X is coded by X itself and members of X and members of the transitive closure of this thing, and finite sequences of ordinals. Okay, so those parameters, those other parameters.
So this is some basic fact from how the constructible universe looks like. Okay.
Yeah, and then this implies that the parameters that we can always pick, that we can always assume parameters come from this set, yeah? Positive closure of X union X cross alpha to the omega. So basically, you can always pick parameters from there. Okay, so that's how I pick P sigma. The formula, there is a formula because there's some formula works. So there is a formula, and then the parameters are the type that I mentioned. Okay, so what does this? So where are we? We are now. We fixed the real parameter, right? And now we have to look at what we are defining is a real number, right? So we have to say, look at the set of sigmas, the set of the real for which each integer is definable for measure 1 many sigma, right? So go by integer. So let Dn be the set of sigma in C, right? Let's see, C is the set of points for which x0 can be picked to be can be used as a parameter, right? And okay, so first let's make, so let for sigma in C, y sigma be the set of n such that L alpha sigma A intersection sigma sigma satisfies phi sigma A phi, well, how did I write n? Can I just look at the order? N P sigma is okay, so N P sigma A intersection sigma and x0. So it's the real that we define. And now we ask, okay, so now let Cn be the set of all sigma such that n is in y yeah. Sorry, I want to pick, I want to say, now let y in R be given by n is in y if and only if the set of sigma in C such that n is in y sigma has measure 1, right? And for some, we have the set of sigma in C such that y sigma is exactly this y is measure one, right? And then we are done. But now I can put this y inside sigma. There's just one real. So I guess and not so. And instead of sigma in C such that y is in sigma is also measure one. So contradiction. Because y sigma is not in sigma for all of sigma in B. Right? Right, that's what you do. Okay, so that's what did we prove? Ah, yeah, I just proved that the reals stabilize, right? For a measure one many sigma. Okay, so what happens if I take the product of these guys? That's the next important lemma in this line of arguments. If you take the MA sigma model mu, then
Gregor, that's a maybe stupid question, but could we just show that the set of sigmas such that RMA sigma equals sigma is a club, and then since you know that this measure concentrates of clubs, say that it has to be measure one, because like it's kind of obviously you can catch your tail and because the argument.
well, you have to. You cannot prove it's a club, right? And you don't have choice. So you have to take.
Yeah, but why do I need choice for that? Because I just take whatever reals. Ah, because the reals of the next model, I would have to collapse it somehow. Okay.
So definability over. You could do another argument. You could force with collapse omega 1 of R.
Uh-huh.
And then in that universe, the set of such sigma
It's countable already. Right.
is club.
Uh-huh.
Right?
Yeah, I was thinking of the situation.
And then you can argue that in V, if the set of such sigma is not club, basically you could argue that if the set is club in V, then it would remain club in the extension. So you could probably do something like that. Okay, but I want you to see these proofs. I mean, this is why normality is important, right?
Yeah, it seemed kind of.
So here now we're gonna do. Yeah, so if I now take the product of these things, what I will end up with is L of AR. So how about we prove this? I mean, okay, so we already know that Walsh's theorem is true, right? We already argued like this. Walsh's theorem is true because mu is normal, right? This will allow us to pick when it comes to when you get to the stage when you want to pick the witness, right? You can use normality. The witness, again, it's the same argument, right? You have the set of witnesses that are definable from some points inside sigma, but then on a measure one set, you can pick the same witness. Okay, which means what? So by elementality, this thing is something like L A prime F R prime, right? So I need to show, because these guys were L of this type, right? So need to show that R prime is R and A is A prime. Okay, but that's kind of trivial, right? So what is A? How about I leave this as a homework? Homework, finish. Approved. Right, what you have to do, you have to pick the real in R prime, well, that has a representation. So here is, for example, suppose X is in, well, we have that R prime is a subset of R. All right, let's just do it. So we have R prime is of course subset of R, right? So now pick X in R, want to see X is in R prime. Okay, so what is the function that's going to represent X? We have the set of sigma such that X is in sigma is measure 1. So pick, so let, not pick, right? This is fineness. So let's call this set C. So let F from C into a sigma be given by F of sigma equals to that particular real. So then the class is actually equal to X. Okay. And the other two, so okay, so that shows the real side of the same, but then you can show this is also by the same proof, right? So pick to see that A equals A prime, pick X in, let's say, A, and want to see X is in A prime. Okay, if X is in A, then X, so again, let C be the set of sigma with such that X is in sigma, right? And this is measure 1. So what do we have? So we have the set of sigma such that M A sigma that thinks X is in A intersection sigma, right? This is measure 1. Now A prime is what? A prime is F mu, where F of sigma is equal to A intersection sigma. That's what A prime is, right? By Wash's theorem, that's what it should be. Okay, so we have what? We now have, so by Wash again, we have for measure 1 many places. Think of, right? So this is saying that the constant, by Wash's theorem, we have that the constant function X, I'm sorry, the constant function, right? I already called something C. Okay, let Px be the function from omega 1 of R into reals, like sigma equals X, right? So it's just a constant function. Then Px mu is in, but just look at this. Measure 1 many places, that's true. Therefore, by Wash's theorem, you have to get that this is true, right? Sigma going to A intersection sigma mu, which is my F. And this means that that's just going to be X, and this is A prime. So A is a subset of A. But the same proof will show that the other way, right? Okay, so homework, so A prime is essentially so this is this. Okay, so how are we gonna use this? Well, this one we will use to prove. Remember what we are trying to prove. We are trying to prove this, right? So, for example, to prove that the omega-1 can be pushed up beyond any ordinal less than theta, it's this fact that we will use. This fact. So let's try that. Okay, so claim theta is less than or equal to pi mu omega-1. So proof fix alpha less than theta and let pi be a surjection. So let A be a set of reals such that X in R, which codes this, right? So X codes X0, X1, and I X0 is less than or equal to 5. So it codes this relation. It's a set of reals. Okay, so from A, you get what? You get the surjection. If I know A and I know the reals, then I get surjection onto alpha, right? Okay, so now we consider what do I want to consider? Yes, I want to take trees that project to this. So now, so by ADR, okay, this is a fact that we have to borrow from ADR. There is a tree on some omega cross kappa such that A equals projection of B. Oh, okay, but I want a little bit more than this, I think. What exactly I want to show? I want to show that for measure 1 many sigma yeah. Yes. So I think I want to do a little bit different. Yeah. Okay. So right. Why do I even need this? I don't need this tree. Okay. I think it's coming up probably in the other direction. Okay, so what do we do now? We take, so now let theta sigma be the theta of MA sigma, which is theta of LA sigma sigma, right? So theta sigma is a countable object. We have, because sigma is countable, theta sigma is less than omega-1. Remember, for measure 1, for all actually, we have sigma is the set of reals of the structure. Theta is the least ordinal such that you cannot subject sigma onto, right? inside that structure, but sigma is countable in V, so it has to be countable. Right? Okay, so anyway, sigma, so this object is countable, which now gives me a function from, right, so now let f from p omega 1 of r into omega 1 be given by f of sigma equals theta sigma, which is less than omega 1, right? So by wash, we have that the f mu is less than pi mu omega 1. This, remember, pi mu omega 1 is the equivalence class of the constant function that gives me omega 1 all the time, right? But what does this mean? What is this? What is this value? Now we have a set of sigma such that ma sigma thinks f of sigma is equal to theta sigma is measure 1. That means by Walsh's theorem again, right? By Walsh, I just apply Walsh's theorem to this. That means the equivalence class of f has to be the theta of the product, right? So that means the equivalence class of f by mu must be theta of this product, m a sigma mu. But we just computed that this is the same as theta of L A R. Okay, but by ADR, theta L A R is less than theta. I guess I just wanted to see that this is bigger than alpha, right? So I don't need ADR for this. But alpha is less than theta LAR. So alpha is less than, right? The equivalence class of f is the theta. The equivalence class of f is smaller than the image of omega 1. Alpha is less than theta, so alpha is less than pi mu omega 1. Okay. So, I mean, let's try again, yes? So we have, I wanted to prove theta is less than to the image of omega 1. We pick some alpha less than theta, and we pick a set of reals that codes it. Now, what I want to show is using A, I want to define a function that maps countable subsets of reals into omega 1 that will bound, then in the product of the structures will bound where alpha goes, but will be above alpha, right? Okay, so because, so we set it to be the theta of this countable structure we found. Okay, so that, what does that mean? Because the thetas are countable, so you'll end up having f of mu is less than pi mu omega 1. That's just Walsh's theorem. But for measure 1, when sigma f of sigma is less than omega 1, then the equivalence class of f will be less than the image of omega 1. But we also now have this fact, right? So we have for measure 1 many sigma that satisfies f of sigma is theta sigma, this countable thingy, which by Walsh's theorem carries to the product. So you have that the equivalence class of f is the theta of the product, but the product we just showed is exactly L of AR. So that means that the f mod mu is actually this theta, which is bigger than alpha. Why is it bigger than alpha? Because A was coding alpha, right? And so we know that alpha is less than pi mu omega 1. Okay, so this is one direction. This is this direction. Now we need to prove the other direction. Okay, so the other claim is I mu omega 1 is less than or equal to theta. So how we gonna do this? For this, what you want to do is you want to pick a function. So what is the idea here? This is probably a little bit harder. So what you want to do here is you take some f whose mu is smaller than pi mu omega 1, right? So f is a function from p omega 1 of r into omega 1. And we want to show that this cannot be. So want to see that the f is less than theta, the equivalence class. Right? Why is this enough? Because if that was strictly above theta, then some function like this would have its equivalence class would be exactly theta. Okay, so this is what we want to do. Okay, so what do we do? What we do is we have to take this f itself as a set of reals. Right? So why doesn't the same proof work? Yeah, I need to bound how far this this goes, right? So what would be the idea? So you would take, you would try to do the same thing, right? So we want to see that M for the set of sigma such that, so then A code, let A code F, exactly how we will talk. And then we want to say, okay, now I'm coding F, so that means probably that should mean that, right? So we want to have that the set of sigma such that M A sigma thinks F of sigma is within the theta of the structure, right? So it's less than or equal to theta sigma with respect to A, right? So I could just write theta. If we had this, then we would be done because now if you take the product,
So what you want to have is that this is a big set, right?
is in mu, right? So if we had this, then by wash, right, you'll have what? You'll have that the product of these guys, which is L of AR, right? So this would mean that L of AR, which is the product of these guys, thinks that F mu is less than or equal to theta of L of AR. And that is less than theta. But theta L of AR is less than theta. This is, we use ADR for this. Okay, so let me prove. First, I prove this simple fact that if you pick a set of reals, then its theta relative to that will be smaller than the big theta on the ADR, right? This fact. And then we'll see how to do this one. Okay, so the lemma we will use is assume ADR. Then suppose A is a subset of R2, right? Then there is F from such that let's say for every X in R, AX is not empty. right? Then there is a function from reals onto reals. It's called uniformization. Such that for every x in R, f of x belongs to A. Right, so every set can be uniformized. This is called uniformization. And 2, as a consequence of 1, for every subset of R, theta of LAR is less than theta. Okay, so how we do this? For one, you just play. I mean, you let so one plays, right? So one plays a real x, and 2 starts playing y. And then that's it. This is all. Such that 2 wins if x, y belongs to A. And of course, 2 wins. One of them has to win, and 2 wins, because 2 cannot lose. If 1 wins, then one's play is determined. It's only one move that one makes. But then, because whatever move one makes, right? 2 before, if 1 wins, 2 already knows what one's move is. Okay, then 2 can just pick a point from the corresponding set. So homework, right? It's easy homework. 1 cannot win. So 2 wins, but if 2 wins, it's a strategy. But 2's strategy is the F we want. Right? What is 2's strategy now? 1 plays x, and f of x is going to be something with the property that we want. Okay, so this is very easy. Now 2. Okay, so imagine, suppose theta is equal to theta of L of AR. Right? Oh. So this means, so our set of reals is actually equal to the power set of reals of L of AR. Why? Because each set has weight rank, right? Because if B subset of reals and weight rank of B is say alpha, then there is some C in LAR whose weight rank is exactly that. Such that the weight rank of C is exactly B, but then B is actually inside LAR. Because if 2 sets have the same weight rank and you have all the reals, then you have the set, right? Because being the same weight rank means you're continuous pre-image. And via a stronger form, right? There's a winning strategy that witnesses. So if you have all of the winning strategies and you have all the reals, and you have your set C, so you will get B.
Sorry, do you want to write here that the rank of C is equal to rank of B?
Weight rank of C is, or yeah.
Okay.
Right, because remember the theta is the supremum of the weight ranks. So if you have some set of weight rank alpha in the other hierarchy, you can pick another set of that higher rank, weight rank, but they're comparable because it's the same. The reals are the same. The reals of V and the reals of LAR are the same. So the weight ranks. The fact that the weight ranks are the same means You have all the sets of reals you want. Okay, so we have all the powers, all the sets of reals in LAR. But now we do the usual trick, right? The diagonalization argument. So let's now notice. Okay, well, so we now do the diagonalization. Consider B, which is the set of pairs X, Y, such that LAR thinks X is not OD from Y, right? So B is definable in LAR, so B is in LAR. We have, well, we already argued that power sets are the same. So B is in LAR, but every set is in LAR. Every set of reals is in LAR. But now B can be uniformized, right? So we have from uniformization, we have some F from reals to reals, such that well, why does uniformization apply? Such that for every X in our X, f of X is in B. Why does the uniformization theorem apply? It says, let's just go back to uniformization, right? I need to know that the sections are not empty, right? So why are the sections not empty? Well, pick an ODA. Sorry, guys, ODA. It's very important. You're allowed to use A as a prompt. Why are the sections not empty? Well, you cannot, because determinacy holds and OD sets, if X is, pick your Y. We want to see, sorry, I should say Y is not OD from X. Y is not ODA from, so I want to uniformize. Okay. So pick an X, why is there Y which is not OD from X? If every real was OD from X, then you'll have a well ordering of the reals. But determinacy holds, so you cannot have well ordering of reals. Right? Because R is not well orderable, we have that for every X in R, Bx is not empty. Okay. All right, but F is where?
How exactly do we use determinacy? But in saying that R is not well orderable?
Why is it that R is not well orderable?
Yes, under determinacy.
For example, Baire property holds.
Aha.
So you have, if Baire property implies reals are not well orderable because of the Kuratowski-Ulam theorem.
Aha.
Yes. And perfect set property holds, so you know. Or every set is Lebesgue measurable. Maybe that's the easy one. There's always a right. If R is well orderable, you have a non-Lebesgue measurable set of reals. That's easy to see. So you have. But now think. I mean, where is F? F, because F is a set of reals. F can be coded as a subset of R, right? Because it's just a set of pairs, and pairs can be coded into one. So we already argued that the PR is the same as PR of L of AR. So F is in L of AR because all sets of reals were belonging there. Okay, but everything in L of AR is ordinal definable, but L of AR satisfies every set is OD from A is OD from A and a real. So that's because of this constructibility fact I mentioned earlier. That's the sigma 1 function. That, yeah. So the parameters you will need are A and some real. So F is OD A from Y for some X for some X in R. But now we know that what? But f of X, which, right? What is f of X? F of X is supposed to be something that X, the pair X f of X is in B. B tells you that f of X is not supposed to be OD from X, right? So you have f of X is not OD A from X, contradiction. Right. Okay, so this was sorry. So this is what did we prove? We proved that the theta. We proved this, right? And so all I have to do now is show to you that the equivalence class of F is below the theta of L over R. Okay, so we need to show. Okay, so we need to find A such that the equivalence class of F is less than theta LA or equal to theta LA. Okay, so what do? We use another pretty standard trick. We're gonna take A that codes F. So first of all, let A0 code F. In what sense? Right. So A0 will be a subset of R2 such that if XY belongs to A0, then I have too many F's. This F is not the same as the F. This F, remember what this F is. This F is a function like that, right? It's mapping countable sets of reals onto ordinals less than omega 1. Right? So this F maps countable sets of ordinals into omega 1. Okay, so we now look at xy such that then x codes some sigma, which is in k omega 1 of r, and y codes f of sigma. So how can x code some countable set? Well, you can use primes, for example, right? Look at the coordinates of x. My powers of the primes, for example. Okay, that makes sense, right? And why can I say y codes f sigma? Well, f sigma is a countable ordinal, so of course there is some real number codes the countable ordinal. Right? Okay, so this is my A0. Why is this not the A? Well, I want to be correct about well, maybe this would already be enough. So let's just make this our A. This should already be enough. This should already be enough. If not, then we will change it. Okay, so what I need to do now, there's a fact from ADR that I have to use, and I cannot prove this. So lemma, or a theorem actually. ADR implies every set of reals is Suslin, right? we are tree. In fact, in fact, for every A, there is kappa less than theta and T on omega equals kappa such that A equals the projection of T. So the tree lives on something less than theta. I mean, this is not an easy theorem. Cannot do it. I think it's not easy. Yeah, you have to probably. I mean, the only proof that comes to mind is the proving homogeneously. So proving stronger fact, in fact, which is not easy. Okay. Okay, so assuming this, what I want to do is now look at T, right? So consider
Gregor, sorry, what is not an easy fact here?
what? Can you say again?
Which part is not an easy fact?
That the ADR implies every set is
Of real
system.
but isn't this I'm confused because like this seems to be literally part of AD plus, right? So it doesn't ADR.
AD plus does not imply every set is system. AD plus implies every set is infinitely Borel.
Okay, sure.
Okay, I might have to change my preamble to this part of the proof because it's in fact seems easier than. Okay, well let's try. Yeah, consider now the structure N sigma, which will be this L T. Well, I guess it's harder. A intersection sigma and sigma. I guess I don't actually have to say intersection sigma. Just look at this structure. Okay. Oh, not the round. It's more like okay. So this contains. Notice that A intersection sigma is actually equal to projection of E in L T sigma. Oh, why? So I mean, one direction is easy. Projection T L T sigma is a subset of projection T, right? Which is A. So one direction is easy. Now suppose X is in A intersection sigma, right? So X is in projection of T. But this means, so Tx, which is what? The set of little s in kappa less than omega, such that X restricted to the length of S and S belongs to T. Right, so this is the section of T that's relevant when you look for a branch that pairs with X. Right? So this tree is well founded. Okay. In V. It says well founded in V. is ill-founded. Sorry, is ill-founded in V, but ill-foundedness that would be absolute, right? So L of Tx thing T sigma thinks that Tx is ill-founded. If it was well-founded, then we would find the map onto ordinals, right? So I'm cheating a bit. Can you guess where I'm cheating? I guess I'm no. Well, do you need TC when you define the well-foundedness?
Well, depends, I guess, but this is trion, actually
Ordinals.
this,
Yes,
yes,
yeah.
this is trion ordinal second of leftmost, right?
Right. You don't need this. Okay, so this is ill-founded. So X X belongs to projection of in L3 sigma, right? Because if Tx is ill-founded, then you have a branch that witnesses X is in the projection. Okay.
But where have you used that X is element of sigma?
Here, that X is in sigma. Otherwise, Tx doesn't make sense in this line.
Aha.
Right.
Okay.
Yeah. If X is not in sigma, T sub X does not make sense.
Okay.
That's a good question. Okay, so I mean now what we know. M sigma, MA sigma is subset of L T sigma. Yeah. In fact, it's in there. It's a class of. So MA sigma, which remember it was LA intersection sigma. Sigma is a definable class of L T sigma, right?
Carl, one quick question. So, do you like?
Just let me just say this, and that's because
Okay.
A intersection sigma is defined by this formula. It's projection of T. Right. Go ahead.
So, is there? Can you see that every set of reals is in ADR in other way than just by showing that every set of reals is homogeneous?
Yeah, but that's a difficult theorem.
Yeah. Okay. But but there is no like simpler. That's
I
what I was.
don't. Nothing else comes to mind. I think
Okay.
you have to use
Okay.
the partition property. That's, or I mean, yeah, or maybe the derived model theorem. So I mean, it's. I think it's not an easy theorem. Okay. But if you want to learn, I think Paul Larsen's book has the proof on AD plus.
I mean,
I
the
think.
derived model theorem last section has a proof that every set is.
Okay. Yeah, that also has. That's right.
And it's like kind of on the level complication of the rest of the paper. So I guess very hard, but within the range.
I don't think it's very, very, very hard, but it is. It's. I mean, you have to do something, right? You have to prove this. Yeah. So you have to do something. Okay. So we have this. We have that MA sigma is a definable class of L of T sigma. So that means theta of MA sigma is less than or equal to theta of L of T sigma. Okay. So remember this. At this point, it's probably a good idea to remember what we're trying to do. What was the idea? Where is my? This was the This is the idea, right? We wanted to find f, right? So f was some function that maps to omega-1. We want to show that its class is smaller than theta. Okay, so we're going to code f by some set of reals, and then show that f of sigma will be less than or equal to theta a sigma. Okay, and then that would translate into this. So that's what we want to. We want to bound the f of sigma by some ordinal which we can control. Right. Okay. So I guess our idea has to change a little bit because we'll show it smaller than this one. All right. Now what we claim is that for a set of sigma such that f of sigma is less than or equal to this data is measure 1. So it's I'm changing the proof a little, the sort of the main idea a little bit. Proof. So the notice. So let G be all omega sigma. So first of all, I want to work with sigmas for which, right? So let C be the set of sigma such that the reals of LT sigma is just sigma. So as before, C actually is measure 1. So we're going to just work with those sigmas. Okay, so pick a sigma now. Fix sigma in C, and now let G omega sigma be called omega sigma generic over L of T sigma, right? It's an enumeration. Now we have that theta of L of T sigma is equal to omega-1 of L of T sigma G. I mean, if you're used to this kind of arguments, it's easy. If you're not used to it, then what is the intuition? Well, everything below theta is surjective image of sigma, right? And we just collapsed sigma. So therefore, everything less than theta L of T sigma must be countable. But theta L T sigma is a cardinal of L of T sigma, because if it wasn't a cardinal, so something smaller would be surjecting onto it, but anything smaller is surjective image of L of T. So we have to do, so show is omega-1 of L of T sigma G. What do you have to show? First, theta of L of T sigma is a cardinal of L of T sigma. Why is it a cardinal? If it's not, then something smaller surjects onto it. In fact, it's a sigma cardinal, right? Sigma cannot surject onto it, and nothing smaller can surject onto it. Because if something smaller surjects onto it, then sigma surjects onto that, and okay. And so we call omega sigma has the same cardinality, right, as cardinality of sigma in L T sigma. So here you use something like chain condition type of argument. Remember, choice doesn't hold, so it's you have to think a little bit. You have to do the usual preservation arguments that you do when you like chain condition type of argument, but without choice. So you cannot pick maximal antichains and things like that. But what you do is you imagine you have you have, imagine theta is collapsed, right? It's countable. That means you have a function, a name for a function from omega to theta. Okay, but then different conditions will be giving values to different integers. But that means you now have a map from col omega sigma onto theta in V, in L of T sigma, right? But that cannot happen because there is a surjection of sigma onto col omega sigma. So this is a sort of a standard preservation argument, but you implement it without choice. Okay, so that's what we have. This is the key thing that we want to pick from here, right? And so how are we going to use it? Well, we want to now argue that yeah. So now let's see. So pick X in L T sigma G such that X codes sigma. And there must be Y. Yeah, so this is what, how you know that there is a Y. Right, yeah, so I wish I picked the T correctly. Now, I cannot quite do that. No, but I can. Right, so I want to say there is a Y. Yeah, I can. There is a Y in L is sigma G such that X Y is in the projection of T. So not really XY, but X join Y, right? Which is the real Xi if I is even and Yi is odd, right? Then X plus Y is in the projection of T. Remember, T is projecting, right? Recall, at this point, recall that A is projection of T, and A was coding something about pairs, if you remember. Let me just remind you what A was. This is A. So it's the set of X, Y. So we're thinking of A as a set of reals, right? So it's a set of X, Y such that X codes sigma and Y codes epsilon. Oh, so I already defined A as a pair. So why don't I just say, okay, let's forget this business. So I define A to be set of pairs such that X, Y is in the projection of T. Why is this? Well, X codes sigma, yeah? And T has how many coordinates? T has 3 coordinates. So we do the same trick. We look at T sub X or Y. T sub X is ill-founded in B, right? Because there's always, if X codes sigma, then there will be some Y which codes the value of X. Because there is Y such that f of Y is equal to, such that Y codes f of sigma, and so XY belongs to A, which is the projection of T. That's why. So if I pick an X that codes sigma, then I will find Y such that the pair XY belongs to A. Okay, so if Tx is all founded in V, Tx is all founded in L of T sigma. So L of T sigma G means Tx is ill founded. So there is Y in L of T sigma intersection sigma, there's a real such that xy is in the projection of t as computed by L of t sigma g. Okay, but what is now y? What does y tell me? But f of sigma, right, is equal to the ordinal coded by y. By y, which is less than omega 1 of L of t sigma g. But that means what? That means f of sigma is less than the theta of L of t sigma, because this omega 1 was exactly theta. Right? Remember? Yeah. Theta L of t sigma is exactly omega 1 of L of t sigma. And so here we found, after collapsing sigma, we found y, which codes f of sigma. And so f of sigma has to be less than omega 1, but omega 1 was theta. Okay. All right, so this implies now what? So we have a set of sigma such that f of sigma is less than theta of L of t sigma is measure 1. But that means, so that means that the f mu is less than, if you apply Walsh's theorem here, you're going to get theta of L of I mu t reals, right? And then, okay, so that's an extra lemma, which we have to prove the same way we proved the other thing. So theta of L, that's a set of ordinals, right? So assume ADR suppose S is then theta of LSR is strictly less than theta. It's the same proof. You're going to assume that they are the same, therefore they contain power set of reals. So you define, you don't need this, any set. Well, okay, let's say set of ordinals. So it's the same proof like the one I gave you. You start with, right? You assume that the thetas are the same, therefore L of SR will contain all sets of reals, and then you define the set of pairs x, y, such that y is not ordinal definable from S and y, and then you uniformize that and then get a contradiction. So it's the same proof like before. Okay, all right, so it's okay, what did we get now? We got that this is less than theta. That lemma tells you that, so finally f mu is less than theta because of lemma. Okay, so we proved that the image of omega 1 is theta. I don't know if you remember what we are actually trying to do. We're trying to get a dense ideal on omega 1 in after by forcing of a minimum amount of ADR plus the inner regular, right?
So
Yeah.
you can maybe remind why this today's result, why is it like key step?
Yes, because
phi.
we are trying to prove that there is an omega 1 dense ideal on omega 1 in this forcing extension. Okay, dense ideal on omega 1, that's going to send, if you think of generic embedding, that means you're getting, omega 1 has to get mapped to omega 2. And okay, so our forcing extension was collapse omega 1 R times, star coin subset to omega 2, right? Okay, so that's something we need to verify, that omega 1 goes to omega 2. And well, who is omega 2? It's theta. So if we force, like, if you do the forcing,
What? Sorry, why omega 2 is?
so if V satisfies ATR
Mhm.
plus theta is reg plus V equals L of power set of reals. Right, then V whole omega 1 R a coin subset to omega 2. This satisfies that theta of V is omega 2. For the same reason that because we well ordered everything, the reals of order type omega 1. Right? So here, think about that. V call omega 1 R satisfies that theta is omega 2. The other thing is not going to change this fact because it's close enough. Why is this? Well, because you well ordered reals of length omega 1. So that means every ordinal less than theta now has size omega 1. Right? Because every ordinal less than theta was a surjective image of reals. Okay, but then you have to argue that you don't collapse theta itself. Okay, but that's, again, it's one of those chain condition arguments without choice. So we have this forcing called omega 1R is a surjective image of reals, right? It's a countable, it's a what are the conditions? Countable functions, a function from a countable ordinal onto reals, but that's just you can call it as a single real, right? So call omega 1R is a subset, can be coded as a subset of reals, but that means you're not going to collapse theta by sort of general forcing theory. I can do that next time. I can, if you're feeling uncomfortable with this, I can do it next time. Okay, but that's why it's important that we need to know that omega 1 gets mapped to theta, because that's what we are, as part of proving that the ideal we end up getting, that the supercompactness, remember we are trying to show that the supercompactness measure, the solid wave measure itself, turns into the into this dense ideal. And so one of the properties we have to verify is that omega 1 gets to omega 2. And then it's used in one of the other proofs. So, okay.
Okay.
Yeah, so if you feel uncomfortable with this,